There are a few. There's like a handful. It's not the majority, but there are a few. All right, so I'm going to start with this differential equation. Okay? I'm actually going to eventually show you the solution to it. And then if we have time, I'm actually going to show you how to solve it. And if we don't have time today, I'll show you tomorrow how to solve it. But right now, what we want to focus on is the picture of what this differential equation looks like. So in order to think about this, you have to think about what it says. It says that the derivative is equal to negative x over y, or the slope is equal to negative x over y. So we're going to pick some points, and we are going to make a chart that's full of those slopes. So let's pick some points, integer values. It can be first, second, third, or fourth quadrant. And let's keep like the values like, I don't know, less than 4. So you can pick an x and y value. They don't have to be the same. All right, and we'll take a look at what the slope is. All right, so the important thing to notice here is that the slope is always changing. It's always going to be different depending on the x and y values. So, Arnie, pick an x and y value for us. 1, 2. And if the point is 1, 2, then the slope is equal to negative 1/2. So the rule tells us the slope is the x over the y coordinate negative of that. So the slope is negative 1/2. All right, Drew. Pick a point. Yep. Preferably first, second, third, or fourth quadrant. Integer values less than 4. 3. Integer values. 3, 2. All right, so what's the slope going to be for 3, 2? X over y. So 3 halves. So I know it's the beginning of the day, and I know it's like a little bit of a slow start. This is supposed to be easy. Okay? Katie Rumor. Pick a point. Okay, just so you know, like Alicia, you're going to be next, then Julia. So you can pick the point in advance so you don't act surprised. All right, so what do we have, Katie? 2, 2. What's the slope going to be there? Thanks. Alicia. 4/3. What do we have for a slope? Negative 4/3. Julia. 4/2. Slope? I'm going to call it negative 2. All right. How about some values on the x or the y axis? All right. So Morgan, can you pick a point on the x or y axis? Like negative 4, 0. That's fine. What's the slope at negative 4, 0? Undefined. Right? Over 0. Undefined. As a matter of fact, can you generalize from this point? Yeah, for any point on the x-axis, right, negative 4, something, 0, the slope's going to be undefined. And what does an undefined slope look like? It's a pole. It's a straight line. Sorry, so we're talking about, I should say, an undefined slope. So we know the slope's going to be something over 0. It's true that at a hole or a corner the slope is undefined. But what we're really saying is when you have something over 0, that's the slope of what kind of line? Vertical line. Vertical line. Okay, so this is going to be a vertical line. How about something, Kelly, on the y-axis? What kind of point do you want to pick there? 0, 2. All right, 0, 2, and what's that slope going to be? Simplify it for me. 0. And what kind of slope, what kind of line is that going to be? Ooh, that's weird. Yeah, as a matter of fact, to generalize, anything along the y-axis is going to be a horizontal line. All right, Rachel, pick a point.
1, 3.
Slope?
1,
right. Ian?
4, -4.
4, -4. So we're now in the fourth quadrant slope.
Oh, sorry, was I not supposed
No, that's great. I was waiting for someone to do it.
I'm going to say 1.
All right. Katie? Slope? As a matter of fact, this looks a lot like Katie Rumors, right? 2, 2 gave us a slope of -1. 3, 3 gave us a slope of -1. As a matter of fact, any same coordinate like 1, 1, 5, 5, -1, -1 is going to give us a slope of -1. All right, Sam?
3, 5, -3.
That's fine.
Okay.
And David?
2, 3. Or 2/3.
-2/3. All right, so I'm going to go and get a graph now. Let's see, I hope I can get a graph. And I'm going to start drawing those in. So graph, rectangular grid. Oh, that's not what I wanted. Okay, that'll work. And I'm going to go... and grab that graph. Okay, and then for each of those points, I'm going to start graphing. So you will remember if we had anything comma 0, I had little slopes that were undefined. And what I'm going to do is I'm going to just draw little line segments that are vertical along the x-axis. So for any of those points, the slope is undefined. And I'm not going to draw a complete vertical line because it's really just at that point that the slope is undefined. What about at 1, 1? What was the slope there? -1. And I'm just going to draw a little line segment. Does that look like it has a slope of -1? And as a matter of fact, wasn't it anywhere along here that had a slope of -1? How about 2, 1? What was the slope at 2, 1? -2. So that's going to have a slope that's a little steeper. As a matter of fact, let's see. What about at 1, 2? What's the slope going to be? -1/2. Let's see. At 1, 3, the slope was -1/3. So that's a little less steep. This would be -1/4, even less steep. At 2, someone picked 2, 3, right? -2/3. So that's not quite 1. So maybe something like that. And that was -3/2. And let's see, at 3, 1, 3, 1, it's very steep, right? It's like -3. It's pretty steep.
Oh, is that what that thing is? Right there?
Yep. What did we say on the y-axis? What are the slopes when I do like 0, 1? The slopes are 0, so I put in a whole bunch of little slopes like that. And I'm going to fill in over here. The slopes all here are +1. And that's going to look like that. And here's what we're doing. We're actually drawing a roadmap of what this differential equation, what the solution to the differential equation is. How do people feel about that? Do people feel like if this were a map and these little slopes were telling me which way to go and I followed them around, like this says go here, this says turn here, this says go straight, this says turn down, this says go down there. Now my circle's not looking that great. That's saying go over, hey, bend around over there. It's an Easter holiday extravaganza. It's supposed to be a circle. That's pretty bad, though, huh? Yeah, yeah, that was horrible. There's no two ways about it. I ended up needing to do something like, more like this. And look, I didn't draw a little slope line here at this point, because we only did integer values, but you can pick any point to draw a slope line, and if I did, you can bet that that slope would be a little bit like that, all right? And so this is called a slope field because it gives you a visual interpretation of what the solution would look like. And so what we're showing you right here is that the answer to this differential equation is a circle. Do you want me to prove it to you? Say yes.
Yeah.
All right. So we saw it in terms of a picture, but if we were to do it, if I were to say, hey, x squared plus y squared equals, all right, where r squared is a constant, is the solution. If I asked you to take the derivative of this, what's the derivative of x squared? What's the derivative of y squared? Careful. Do you remember that? From implicit differentiation? The derivative of r squared? 0 or 2r? 0. It's a constant. Okay, I'm going to solve this differential equation. I'm going to solve this derivative equation. And I'm going to get y prime is equal to negative 2x over 2y, where y prime is equal to negative x over y. All right? So, now the only way we were able to do that is because I knew it was a circle. Yeah, so the question is there a way to go backward and get the fact that it's a circle? There is, and I'll show you maybe tomorrow. So, right now what we want to focus on is the fact that you believe me that this picture is a visual representation of the solution of a differential equation. Do you believe me? All right.
No, not yet.
Thanks. Thanks. Let me show you how your calculator can do it, and then we're going to talk through some problems. All right, so yep. So I'm going to start by going to zoom decimal, zoom 4, and go to y equals and clear out all my equations. All right, so I think starting with a clean window that zoom decimal is going to help us here, I think. So in y1, I'm going to type in negative, not minus, but negative x over alpha 1, which is y. So I'm going to actually type in negative x over y. Gesundheit. Gesundheit. Now, whoops. What happened there? Now, if I were to try to graph this just right now, like, it wouldn't work. It probably has some value stored as y. It would graph like a linear function. Or nothing would happen that I wanted to happen. But if we go to second quit, go to the home screen, and we go to our programs, and you're going to do 6, which is slope FLD. All right, so if you select slope field, now Arnie, you have a way of doing this, and I don't know how to do it. But you have a mode that's called differential equation mode. You hit enter, and it's going to ask you how many marks, how many little slope lines do you want going across and going up and down. I usually pick like 10 for going across and 10 for going down. And that usually works. Sometimes I have to go back and like fix it. And it now will take that equation that you had and it will draw all the little slope fields. And so that's what the picture ends up looking like. Now, I have to be honest, this looks more like an oval than a circle. And if I wanted it to, I probably should have done like zoom square. If I did this whole thing again and did zoom 5, and then went back to my home screen and ran the program again, and did 10 and 10, I think it would look more like a circle. That looks a little more symmetric, I guess. Not really. It looks the same. That's weird.
Did it not look like a circle?
Well, I just thought it looks a little more oval. Like, doesn't it feel like it's stretched a little more along the x-axis? Maybe not. All right, fine, great. It's a circle. There you go. And my hope is that you can sort of see the solution to this differential equation might be a circle. Do you know what it definitely is? No. But it's a way of sort of approximating what the solution might be. David?
Why are there like 50 bazillion different lines? Like, why isn't there just like lines in the middle?
Say again?
Why is the slope field like all around spring and the circles in the middle?
No, actually, and I'm sorry I didn't make this point before, this slope field actually has an infinite number of solutions. If I go back to this, it could be, remember it's x squared plus y squared equals r, it could be this circle. Or it could be this circle. Oh, that's a bad one. Boy. And the idea is that the slope field won't give you an exact answer. It actually gives you a general answer. X squared plus y squared equals c. Hey, how are you looking for? He's here. There you go. All right. So it actually represents an infinite number of solutions to this differential equation that all are in the family of x squared plus y squared equals something. And that's why we get a bazillion number of lines that all look like if you were to start somewhere and follow the map, you go around in a circular fashion. Is that all right? Okay. That's a good question. I didn't say that, and I'm glad you made me say it. All right. So let's see if we take a look at our classwork. We'll do some matching. And we're going to start with 17. Let's see. 52. Okay. So here we have a bunch of slope fields and a bunch of differential equations in 17. And we want to try to figure out which slope field matches which equation. Now, we could, with the slope field program, just enter it in the slope field and get a picture out. And we'd be able to match it, right? I want to show you that there are ways of doing it without using your calculator. All right? So, like, for example, if you look at A, y prime equals x, that's a differential equation that you can actually solve in your head without needing anything fancy. What's the answer to that differential equation? 1/2 x squared. Isn't that it? Doesn't 1/2 x squared have a derivative that's equal to x? Is that okay? Okay. So if you looked here, do one of these slope fields look to you like it would be a road map of 1/2 x squared? I'm hoping the answer is yes. Which one looks like it's the road map to 1/2 x squared? Oh, you know what you left off? Plus c. Did you say that? Oh, good. Plus c. So which looks like a road map to 1/2 x squared plus c? I think 1's opening telling me to do this. I think 4 is telling me to do this. And I see that as being the solution to 1/2 x squared plus c.
So basically you should just like anti-dramatize it and then...
All right, well, it works sometimes. So let's do it one more time where that works. All right, let's do B. All right, so fine. David, what would the what would the solution to this be? Don't stop there. Negative x squared plus c. Perfect. So David says, look, so what? This is 4. This is going to match with 1. All right, so this is the parabola opening downward. That's what that road map is. We're gonna do the next two, but before I do the next two, can I ask, is there anyone that's completely confused and just thinks there's like a bunch of random lines and doesn't see how the function fits with the lines? So far, so good then? Okay, all right. So I'm just putting it out there. Some students find this like a little challenging. There's some students that are like, oh, this is a piece of cake. Other students are like, I don't see it at all. I don't know what you're talking about. And if that's the case and you don't want to say it now, you can just find me and we'll talk through it. All right, now, Morgan, we have a problem.
Yeah.
C, we can't do in our head. No. You can, and that's fine. But actually, you know what we might do first? If you jump to D and you ask Julia, what's the answer to D? No, you wouldn't say that.
Oh, they're the same thing. Yeah.
Kelly remembers what you said. Didn't you say that? Wasn't that you? The answer to D, the derivative equals the function, is e to the x. Right? Which one looks like it could be e to the x? 2. E to the x plus c. And there's actually something funny happens here. If we go below the x-axis, that's a little different. We should put that on hold to think about why above the x-axis it totally looks like e to the x plus c, but below the x-axis it looks a little different. Negative e to the x? Right? And where did that negative come from? Okay. Well, all right, fine. Yeah, it's not quite the right reason, but all right, I'll take it for now. All right, the other thing I want to tell you is, and maybe this goes exactly along with what David was saying. If we look at D, y prime equals y, whenever y is positive, what's going to be true about the slope? It's going to be positive. So whenever y is positive, all the slopes should be going up and to the right. Whenever y is negative, what's true about the slope? It's negative. So whenever we're below the x-axis, the slope should be down and to the right. And that's true. And I'm actually going to use that reasoning to try to tackle C. Now, we know what the answer to C is, right? 3. Thanks. We know that the derivative is the product of x and y values. In the first quadrant, what happens when you take the product of the x and y values? What should be true whenever you're in the first quadrant? It should always be positive, because you're doing a positive times a positive. Is that consistent with all these slopes being positive? It is. What about in the second quadrant, when we take x and multiply by y? You're going to be taking a negative times a positive. It should be negative. Is that consistent with all these slopes? Are they all negative? Yeah. How about down in the third quadrant? Negative times a negative, that'll give us a positive. Consistent with these slopes? Yep. And then in the fourth quadrant, it's going to be negative. So you can actually think through some of these slope fields to make sure that it makes sense. And if logically it makes sense, you can find a match. Do you want to ask a question, or we do more matching? We're going to do more matching anyhow, but do you want to ask a question before we do more matching?
This is like,
You sure?
yep.
Okay. And all right. Let's take a look. All right, so we have a couple more matching to do. I don't think so. 16 was sort of what we did with the circle, except it's more of a self-guided thing. Like if I didn't want to do the circle, I could have said, hey, everyone do 16. We're going to talk in a minute. But I didn't. All right, who wants to start? There are a couple that you can do in your head and a couple that you can't. Sorry, there's one that you can do in your head. And there are a few that we're going to have to think about a lot. Which one can you do in your head? Can't do A or C in your head. I think you can do B in your head. If the derivative is sine x, what's the function? Negative cosine x plus C. And that totally looks like this, right? Right? So I think we have a match there. All right, now we need some reasoning for either A, C, or D. I heard enough from you for at least for now, I think. Ian?
For C, you can use the same logic as we did for, I think it was C and the other one.
All right, so in the first quadrant,
It's going to be positive.
always going to be positive. In the second quadrant,
Negative. If second quadrant is the quadrant I think it is.
that's this one.
Okay, that must be negative.
Yeah, so we're going to go positive, negative, positive, negative. So is that going to match with 2?
I would say.
I think so. So just looking at the positive or negativeness of the slopes, I don't even know if positiveness or negativeness is a word, we would match that with 2.
So we could have done that one in our head technically.
All right, fine. I was thinking which one could you get the solution algebraically in your head, but yeah, all right, fine. I think all of these we're going to actually end up doing in our head, so maybe it was a poor choice of words. All right, so we have B and C done. We're now looking at A and D. What's true about the slope in D? Yeah, right? If the slope is always something squared, it's always going to be positive. So you can't have any little lines going down and to the right. And 3 definitely has little lines going down and to the right. So this has to match with D. And process of elimination, 3 and A go together. I don't know how we'd reason through A if we didn't eliminate the other ones.
Well, it's sort of, it has the same terms that like if I answer something, just like asking something.
Yeah, it has some weird, I agree, it does some weird things. It does sort of like this.
Oh, is that
It looks like a tan function.
Yeah.
On its side, like an arctan function, or inverse tangent, if that's more familiar from terminology from last year. Yeah, I don't know. That would be an interesting one. So the derivative depends on the cosine of the y values, and so you might have to plug some numbers in and feel like, oh, well, the derivative is going to be positive here or negative here. All right. Is that all right? All right. So that's the pictures, and as Morgan said, you can certainly, if you want to check your work, you have that slope field program